This is Weighing the Shopping Benefits of a Smarter Refrigerator, and I am Stephen Godell from the College of Charleston. The agenda for our presentation today is as follows. First, I'm going to go over the introduction, then the hypothesis, followed by some related work, then a motivating example, our implementation, our findings, some future work that we could do, and the conclusion. I'd like to start by introducing the Internet of Things and nutrition. The Internet of Things, or IoT, trend provides enhancements to our everyday lives. And the smart fridge is an appliance that definitely has opportunities for advancement. Nutrition.gov states that creating a shopping list before heading to the grocery store can actually improve your health and also save you time and money. I'd like to talk about the current smart fridges that are out there. There has actually been research done about how to identify the items in a smart fridge in the past. This was based on both image recognition and RFID tag sensing. But these methods alone do not allow the refrigerator to know how much of each item is left. Of scales, we can greatly increase the utility of a smart fridge when it comes to creating shopping lists and formulating meal plans. The scales will allow the fridge to know around how much of an ingredient is available to use by the consumer. Knowing the amount of each ingredient can lead to an algorithm that does not suggest a meal that requires more of an ingredient than is currently available. I'd like to present a diagram of what a particular shelf might look like on a smart fridge with these capabilities. You can see that we have 4 cameras, one on each end. This is to properly tell what items are inside of the fridge. We also have a grid of scales on each shelf. These scales would be small enough that you would be able to tell which item was applying pressure on the scale, so you'd be able to properly identify how much each item weighed. And that would be able to let us know how much of each item is left. We have hypothesized that by utilizing an image recognition system as well as weight sensors, a smart fridge can create better shopping lists by accurately identifying the amounts of food within itself. Now I'm going to go over some related work that we used in this paper. ProVisions, Object Recognition Applied to Smart Refrigerators, discusses the usefulness of a scanning system that can accurately identify the products contained within a smart fridge. Our research improves upon the content sensing of the image scanning detailed in that paper by adding scales to it. The next piece of related work we used was called iFridge, an intelligent fridge for food management based on RFID technology. In that paper, they detailed how a recipe recommendation can be formed based on the items in a smart fridge. Our research adapts the ideas of recipe recommendation detailed in this paper to use scales and image processing rather than RFID. The final paper that we used for related work was about enhancing nutrition. It's called A Smart Fridge with an Ability to Enhance Health and Enable Better Nutrition. And it discusses how nutritional dietary needs can be better achieved by using a smart fridge. In our paper, we utilize the ideas within this paper and improve upon them with the introduction of scales. We discuss a motivating example. We all know that grocery shopping is more productive and much easier when we bring a shopping list. But creating a list that properly utilizes the products that we currently own can be a challenge. If a consumer had a refrigerator that was capable of not only knowing what grocery products were contained within it, but also knowing how much of each product they had left, grocery shopping would be a breeze. This fridge could potentially generate shopping lists based on nutritious meal plans, all while prioritizing meals that could be made with ingredients the consumer already owned. I'd like to discuss the implementation of our smart fridge algorithm. And firstly, I'd like to discuss the schema. We had to define a schema so that we could link up the contents of a user's fridge with the contents of the recipes and ingredients that were in the cloud. In this schema, we've got a product, an ingredient, a general product, a user product, and a recipe. The cloud-based portion of this database would be the general product, the ingredient, and the recipe, while the user product would be in a database stored down on the user's actual fridge itself. The user product relates to a product, which relates to a general product. Each recipe has a list of ingredients in it. In order to test our hypothesis, we had to gather recipes and ingredients that went along to make them. If this process were adapted into a real-world system, this part would actually be shared on the cloud amongst all of the fridges. But in order to gather the recipes to test our hypothesis, we used the Food to Fork API. This API provided a list of recipes and the ingredients that were used to make them. 140 total recipes were utilized. 245 total products went into these recipes. Around half of those products were used in multiple recipes. For example, onions were used in 98 of the 140 recipes. Normalization was next necessary. Because the Food to Fork API provided the amounts of each ingredient in each recipe in a non-standard format, we needed to find a way to convert them all into grams. In a real system, this would be a little bit challenging, but for testing this hypothesis, we only really needed to generate a reasonable random number of grams for each product. The next step in testing our hypothesis was actually to model a user's fridge. By referencing the mock-up of what this fridge could look like, we opted to define our sample fridge as having either 3, 4, or 5 shelves for a small, medium, and large size fridge. Each shelf had a 16 by 16 grid of scales. We used Python to create a script that programmatically built up the user's fridge, and we stored the results of that in a MySQL database table, the user product table, for easy access. This led to the user having around 30 products in the 4-shelf or medium version of the fridge. And by doing it programmatically, we were able to easily build up new sample fridges to better test our algorithms. Next, I'm going to talk about the algorithm that we used. In order to test our hypothesis, we actually needed to create 2 separate algorithms. One algorithm, known as the smarter weight algorithm, utilized the weight of each product that was provided by the scales in the fridge when making its decisions on what to add to the shopping list. The simpler algorithm that was non-weighted did not use this. By defining 2 algorithms, we were actually able to compare the shopping list generated by each one and figure out where mistakes were made when not using scales and weight. First, I'm going to detail the simple algorithm that didn't account for weight. We needed to iterate through each of the recipes in our database. With each of these recipes, we needed to determine the ingredients needed to make it. We put each ingredient in a list. If it was an ingredient that the user already owned, it went in one list, and if it was an ingredient that they needed to buy, it went in a separate list. After all of this was done, we needed to determine which recipes to make and which ingredients to buy. This was simply based on the recipes that needed the least amount of ingredients bought by the user. The more complicated algorithm was the algorithm that actually utilized the scales and the weight in grams of each product. We again had to iterate through all the recipes, and also determine the ingredients needed to make each one. Each recipe again contained 2 lists, one of the ingredients the user has, and the other of the ingredients they still need to buy. But this time, each ingredient contained the amount still needed in grams for the recipe. At the end of all that, we needed to determine which recipes to make and which ingredients to buy. This was again based on the least amount of ingredients needed for the recipe. But we also needed to be sure to update all the remaining recipes' ingredients with the new amount of each ingredient used when we chose a recipe. This way, the refrigerator would never recommend a user not purchase an ingredient that they needed because it was already utilized in an earlier recipe. I'd like to go into a little bit of detail about how these algorithms were coded in Python. So the 2 algorithms were fairly similar, one just utilizing weight from the database and the other one not. So we were able to sort of do the same flow through the program. So first we started out with a list of recipes, which we made sure was clean each time, and also a list of ingredients that were already owned, and a list of owned ingredients that were already used. Each of these lists were cleared each time. We then had to connect to the database and initialize the recipes, which I'll show later. We next initialize the owned ingredients, and then we iterate through each recipe, and we determine the ingredients that are needed to make the recipe. Now this goes slightly different whether or not we're using weight, because the weight determination is used, and it makes the list slightly different, as I detailed earlier. I'm now going to talk a little bit about how we actually initialize all our recipes and our own ingredients from the database. So, as I talked about earlier, we've already loaded up a list of recipes in the database, as well as a list of user products in their respective tables. So before we do any interesting stuff in the algorithm, we actually have to make sure to load these into memory so the Python script can use them. So we're basically here just iterating through all of the recipes and actually storing them in that recipes list. We then iterate through all the ingredients and we add each ingredient for the recipe inside the recipe object as an ingredient. And that includes its weight information and all that. We next initialize the owned ingredients in a similar manner. We're going to go through the user products that are stored in the database and just make sure to put each one of them in that list. Now I'm going to discuss how we actually determine the ingredients needed to make each recipe. So we pass in the recipe that we're trying to figure out the ingredients for, and also whether or not we're using the weighted algorithm. We start with an empty list of ingredients needed, and then we iterate through each ingredient that the recipe calls for. We initialize whether or not we own that ingredient as false, and then we iterate through each of our own ingredients that we've previously built up. If the owned ingredient is the same as the ingredient in the recipe, then we set that we already own the ingredient. But we still have to determine the amount needed so that we know how much weight we're actually using of that particular ingredient. So each other ingredient knows that we're already planning on using this ingredient in this recipe. We then create a new ingredient object and append that object to the list of ingredients that are needed. The code for determine amount of ingredient needed is actually much more useful if we're using the weighted algorithm, because then we actually know the information about the weight, so we can do some better determinations there. Once we get through the for loop, if the ingredient isn't owned at all, we just add the new ingredient as something we need with the entire weight of it, regardless of if we're using weight or not. I'd like to discuss in detail how we determine the ingredients to actually put on the shopping list. This is the last part of the algorithm really here. So at this point we're going to pass in whether or not we're using the weighted algorithm, the number of meals we're actually putting on our shopping list, and then a nice little thing to help print more information if we want it. So first we're going to sort the recipes, and what this code does is basically sorts all the recipes in the database by the least number of ingredients that we actually need from our previous determinations. And then we're going to make sure to actually go through a while loop to make sure we make the right number of meals to add to the shopping list. So we're going to grab the first recipe, and then we're going to cut the rest of the list off so that it doesn't include that recipe, so we don't add the same recipe twice. If the recipe is valid, which essentially means that it has at least 4 ingredients in total, then we're going to iterate through all the ingredients that we need to buy. And if the amount is greater than 0, so we need to buy some of it, then the nice little printing says we're going to buy however many grams of whatever the ingredient was. If we're using weight and we don't need to buy any of the ingredient, then we're going to append that to a list of owned ingredients that we're already using for this recipe. And if we're not using weight, then we do the same thing there, but it's a little bit different printing if you're printing verbose. Finally, if we're using weight, we need to actually go through all of the other recipes and decrement the amount that we need. So we need to add that we need more amount of this ingredient because we're using this amount that we already had in our fridge. So all of the other recipes need to know that that's no longer available for their use. And that's really what makes the weighted algorithm so much better than the non-weighted algorithm. And then after that, we're going to go ahead and sort the recipes again so it's ready for the next iteration of the while loop. At this point, we were able to run our algorithm over and over again 50 times for each shelf and number of meals in the shopping list combination. So we chose to use 3 meal plans, 7 meal plans, 10 meal plans, and 15 meal plans. And we chose a small, medium, and large size fridge. These fridges had 3, 4, and 5 shelves respectively. As you'll notice, there is a trend with the more meals on the shopping list and the larger amount of products your fridge can actually hold, you end up with more mistakes being made. Now, these are ingredients that the shopping list did not recommend you purchase. But in reality, you needed to purchase because you'd already used all of them in a previous recipe that you'd made that same week. By the time you get up to 15 meals on 5 shelves, the refrigerator makes about 4.5 mistakes. Whereas it's not so bad with 3 meals and 3 shells and only about a half a mistake per time. Now again, this paper does actually lead itself to some interesting future work. We could actually augment a refrigerator with scales and cameras and see how accurate it can identify the items within itself and the weights. We could also explore the possibility of equipping a pantry with similar technology for a more accurate shopping list. By going through the process of grabbing a bunch of recipes, a bunch of ingredients, building up a user's fridge, and then testing out how many mistakes were made with a simple algorithm versus a more complicated weighting algorithm, per shelf and per number of meals necessary, we were able to come to the conclusion that utilizing scales as well as image sensing technologies does actually allow a smart refrigerator to create more accurate shopping lists by making fewer mistakes on what foods the consumer already has enough